Okay, good. So now we can imagine we've gotten to like this, for example, and we're like, oh, like now, based on this, we want to make code that does, in this example case, like if is palindrome B1, B2, B3, B4, then toggle C. Like we can imagine like this is our goal, is to make the quantum code for that. So we're going to still do this in a few steps. The next step is to make what I'll call trashy quantum code for doing that. So let's be a little trashy. Okay, so step 3 is to take, and or not code and kind of compile it to trashy quantum code. Okay, so what do I mean by this? It's actually pretty obvious what to do, I think. So I'll just do it by example. We'll do it the example of, we're not going to make, we want to make this, like maybe if is palindrome B1, B4, then toggle C. Given that we got to this code, our goal might be to make this quantum operation. For now, we'll just make the trashy version of this. Trashy. If palindrome, then toggle C. And here's how it goes. So I'm going to write quantum code now. So code line number 0. We should imagine, this is like we're making a subroutine now, and that like B1 through B4 and C are like 5 qubits that are already there. And we want to make like code that manipulates these 5 qubits. But the first thing we're going to do is make some more qubits. We're going to do new qubit, and we're going to make 11 more qubits, W1, W2, up to W11. And why 11? Well, hopefully you can see why. And then we're just going to start basically converting this if and or not code to a code that kind of does the same thing. So in our quantum code, when we do this new qubits, like everything here is going to stay completely classical. Like even though these are qubits, like they're only going to have like regular old bit strings. So when we initialize these qubits, we know they all have value 0. So this instruction, which like sets W1 to the AND of B1 and B4, like we can accomplish that just with like toggling W1 if B1 and B4 are true. So like we can just have if B, all right, capital now because these are qubits, P1 and B4, then toggle W1. And this is a valid quantum instruction. This is our old friend. That's a valid quantum instruction. In line 2, similarly, like not B1. So we'd be like, oh, if not B1, then toggle W2. Again, it's not quite the same as line 2 over there, but again, if you're only worried about bit values and you kind of know that W2 is 0 coming in, then this instruction, which toggles W2 if not B1 is true, is simply the same as setting W2 to like the not of B1. So okay, I'm not going to write it all out, but the next one would be like if, I'm just basing it off here, not B4, then toggle W3, and so forth. And maybe I'll do the last one. The last line 11 would be if W5 and W10. It's good that we know it's an AND now. W5 and W10. Then toggle W11. Okay, and then C is like the final value. So we'll need like one more instruction. We just want to copy, actually, we don't want to just copy the final answer into C. What we want to actually do is sort of toggle the final answer onto C. Like our actual goal is to to see if the final answer is 0 or 1. And if the final answer is 1, we should toggle C. And if the final answer is 0, then we shouldn't toggle C. So like the final step we need to accomplish here is take, W11, which is effectively the answer. And if it's 1, toggle C, and if it's not 1, don't toggle C. So the last line, therefore, is if W11, then toggle C. So that's it for the compilation. I hope you agree that this quantum code has the property that, if you send in just B1 through B4 and C in a basic state with just some bits, then this code accomplishes this instruction, but with some trash. B1 and B4 will end up the same thing. C gets toggled appropriately based on whether or not this was a palindrome. But there is one more additional twist, which is that all these qubits, W1 through W11, now exist. Moreover, if I asked you, what are the values of W1 through W11, you'd be like, I don't know. They have some weird values that depend on what all these bits were. So this is when you're doing regular computer programming, indeed, if you're trying to compute a function, you do very often make new variables, or you're I'm going to allocate some memory because I need more space to do some intermediate computations. And then if you're a very polite programmer in your subroutine, you will then free that space at the end and be you know what, I used this, but now I don't need it. If you're a very lazy programmer, you'll just be whatever. Now the operating system has all these W bits written somewhere, and I didn't tell the operating system that it's okay to get rid of them. But yeah, this is not uncommon in classical programming that you need to get some extra workspace memory or variables to help you out, and it's similar in quantum. The question was, do we need a new qubit for C? No, this instruction assumes that this qubit C already exists. If you look at the name, forget this for a second, it's telling you, but based on its name, that its goal is to toggle this already existing qubit C if and only if these already existing qubits form a palindrome. Okay. So I like to call these W's workspace qubits. This is this extra memory that you allocate. Well, these are 11 extra maybe electrons that you make, or photons, or however you're storing your qubits, in order to facilitate this transformation you wanted to do. In quantum computing literature, they're called ancillas. Somebody decided to give it a strange name, but we'll just call them workspace qubits. And as I said, this sort of, but not exactly, does the right thing. So in other words, we could sort of, if we think about how does this code operate? So in our dreams, ideally, this instruction that we're trying to build, we should map, for example, 1, 0, 0, 1, 0, 2. Okay, so this is, imagine we have qubits B1, B2, B3, B4, and C, and they're in this basic state, 1, 0, 0, 1, 0. What ideally would be the new basic state if we had properly, exactly implemented this? Bearing in mind that palindrome means it reads the same forward and backwards. Yes?
0, 0, 1, 1.
Yes. Ideally, we should have mapped this to 1, 0, 0, 1, 1. Okay, because, well, this instruction is supposed to, on one hand, not actually change B1 through B4, but it's supposed to detect if it's a palindrome, which in this case it is, because 1, 0, 0, 1 reads the same forward and backwards. And then, if it is, you're supposed to toggle C. And it is in this case, so we're going to toggle C from 0 to 1. This is what we really wanted our code to do. But our code does not do this. Instead, we got I will now read off my paper. We got 1, 0, 0, 1, 1. I'm going to write the qubits in this order. You know, after we run this code, we suddenly have not 5 qubits, but which we used to have. We suddenly have like 16 qubits, which I will write in this order. I'll write all the B's, then C, then W1 through W11. And apparently, I mean, maybe I got this right or wrong. I probably got it wrong because I had or instead of and there, but something like this. 1, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1. Maybe. Something like that. Like, all these, we created all these, like, you know, workspace qubits, and they have, like, some weird values. You know, whatever these, really, whatever, like, these intermediate variable values are. And, like, if we put in some, like, different, you know, bits here, like, I don't know, 0, 1, 1, 1, 0, these would, again, be some other, like, weirdo values. In normal classical computer programming, you're like, I don't care. That's fine. I'm only ever going to use, like, I don't know, C. If you also on the side left some memory, junk in memory, you know, that's fine. But let me just say, in quantum computing, it's very bad to do this. I won't try to explain why now, because it's a little hard to explain why it's so bad right now. Later in the course, I'll say, like, hey, let's take a look back and reflect a moment on when we had this, like, you know, trashy quantum code, and you'll be able to see, like, it's terrible if you, like, leave this trash here. For now, I'll just, like, scold you and be like, come on, be polite. Do not, like, leave trash around. Do not leave these, like, qubits lying around. Clean up after yourself. So you might say, well, how do I clean up after myself? You know, in classical programming, I don't know, like, I free this memory. I delete these variables. But we don't have a delete instruction in quantum. There's no, like, delete this qubit. Actually, there is an instruction which is kind of similar to deleting, which is extract all. As I told you, like, if you do extract all, it's really like those qubits get destroyed. Now, we don't want to destroy all the qubits. We just kind of want to get rid of these workspace ones. And so right now, like, we do not have the facility to, like, have an instruction that gets rid of them. But you can leave that in the back of your mind. What I'm going to do for now, you know, to try to do my best to, like, clean up this trash is I will at least try to get it so that we don't leave all these bits in some, like, rando state. We leave them all as zeros. This is, like, the most clean, you know, clean thing I can imagine doing. And I'm going to, you know, exhort us to do that now. So this is good, but, like, let's at least try to end with the W's all zeros. Because it's not really, like, possible to not use W's. Like, sometimes when you do computation, like, you need to allocate some more variables. But let's at least try to leave them all as zeros. So how can we do this? So we still want to, like, you know, toggle C as appropriate, like, based on, let's say, the palindrome nature. How do we get all the W's back to 0? I mean, one issue is, like, again, in quantum, there's no instruction that's just, like, set this qubit to 0. That instruction doesn't exist. You could be like, oh, like, W1 is 1. I better, like, toggle it. But, like, how do you know down here, like, whether you should toggle it or not? Because, like, whether or not you need to toggle it, like, depends probably on the B's and stuff. Yeah? Yeah, backwards. That's exactly right. There's, like, a beautiful fix that makes it, like, remarkably simple. All you do is uncompute all the stuff. I mean, the beauty of these, or a beauty of these quantum instructions is that they have undos. They're reversible. Moreover, it doesn't have to be like this, but by, like, a funny coincidence, like, all these instructions are literally their own undo. We've talked about this before. Like, whenever you do an instruction like this, if you were to do that instruction immediately right over again, it would exactly undo what you just did. So we kind of want to do that because, like, right here, after we created these new qubits, we were almost in the desired glorious state. After we create these new qubits, we're in this, like, state where, like, the B's are what they are, and like the W's are all 0. The only trouble is we haven't actually done the computation yet. So we still got to like, update C potentially, toggle C potentially. But then we kind of want to get back to the situation where all the W's are 0. And we just have to undo everything, except for like this. So, what we do, and this is still part of the mechanical procedure for like taking and or not code and eventually making the quantum version of it. So we add in more instructions. Maybe line 13 is, well, it's the undo of 11. But as we saw, like these instructions are their own undo. So we like do if W5 or W10, then toggle W11. And like line 14, it's like if W6 or W9, then toggle, maybe this should be and. Yeah, this comes from the fact that I got that wrong. Toggle W10 and dot, 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 dot. And then like the second last one, or maybe line 23, is the reverse of this, which is just, if B1 and B4, then toggle W1. Okay, so now this collective code from line 0 all the way down to 23, I claim is more or less this. We kind of got rid of the trash. Yep. Yeah, the trouble is, like, you would love to do that. Like 13, you'd be like, now I'd like to go back and fix the W's down to 0. So like, if W1 is 1, I'd like to toggle it. Or sorry, if W1 is 1, I'd like to toggle it. If it's 0, then I want to not toggle it. But there's no instruction like that. There's no if W1, then toggle W1. I like swore you against that instruction, in lecture like 1 or 2 or something. Because that instruction is actually the same as set W1 to 0. And that's not a reversible, undoable instruction, and so it doesn't exist. Like, if you could somehow know, like, which case you were in based on the B1s, you would know what the W values are, and therefore you would somehow know what to do. But it's not like that. You kind of have to, like, programmatically. In some sense, what we're doing here is, like, programmatically deciding whether or not we need to, like, toggle each W again based on what the Bs were. So, in fact, in some sense, we're implementing your idea. We're kind of using the Bs and, like, the previous Ws to decide, oh, do we need to toggle this one back? So, like, kind of like, this gets us into a state where, like, the Bs are all what they used to be, and, like, the Ws have some funny values, that depends on what the Bs were. This line, like, accomplishes our mission of, like, toggling C appropriately. And now we're like, let's try to get those Ws back to 0 again. And so we indeed, like, we do it in the reverse order, right? Because, like, we have to undo this one, and that gets W1 back to 0 for sure. And then we undo this one, that gets W10 back to 0 for sure, and so forth. And then finally we do this one, and that gets W1 back to 0 for sure. In the sense that, like, if we just, like, imagined deleting this line for a second, then it would be very clear. Like, we did a bunch of instructions, and then we just undid them all. So that would indeed take us back to all zeros. Yeah, any questions about this? This is a great trick. This was discovered in the 60s before quantum computing existed. For some reason, physicists thought, like, oh, there's some physics reason why if you do a physical transformation on, like, a bit, if it's a reversible instruction, then in principle, it does not need to use energy. It's like a physics rule. And so, like, physicists were like, maybe we can make a computer that, like, uses no energy by, like, using only, like, reversible instructions. And they basically discovered this, which is pretty cool. Then they were like, oh, our computers are pretty energy efficient anyway, so never mind.